Hello everyone, my name is Shruti Agarwal. My college roll number is 225056 and my topic is Theory of Field Extension. Now before getting to know what is the field extension, one must know what a field actually is. So let's see. Field. Any algebraic structure F with two operators is called a field if it is a commutative ring with unity having multiplicative inverse of every non-zero element of it. For example, Q, R, C with having two operators are the examples of field. Now what is a subfield? Any non-empty subset S of a field F is called as a subfield of it if S with two operators is also a field. Example, set of real numbers R is a subfield of the set of complex numbers. Theorem related to it, the necessary and the sufficient condition for a non-empty subset S of field F to be its subfield are A minus B belongs to S for all A, B belongs to subset S, and second condition is AB inverse belongs to S for all A, B belongs to S. Now what are the characteristics of a field? For any field F, the least positive integer n for which ne is equals to 0, where e is the multiplicative identity of field is called the characteristic of field. The characteristic of a field is either 0 or a prime integer. Fields with non-zero characteristics are known as modular fields. Now, what are field extensions? Let F be a subfield of field of K, then K field is called as extension of field F. For example, as Q, that is the rational numbers, is a subfield of real numbers. So we can say that the R is an extension of Q. Similarly, C is an extension of R. Set of complex numbers is an extension of the real numbers. Q root 3 is a field extension of Q. Now what is the degree of field extension? Degree of field extension, or we can say the dimension of it. We know that any field forms a vector space over its subfield, hence K over F will be a vector space if K is the field extension of F. Dimension of vector space Kf is called degree of K over F. It is denoted by K is to F. Now let's talk about just a few types of field extensions. Now first is the finite extension. From the word itself, one can guess what does it mean. If degree of a field extension is finite, then it is called a finite extension. Otherwise, it will be an infinite extension. That is, for an extension K of field F, if K is to F is finite, then it will be a finite extension. If K is to F is infinite, then it will be an infinite extension. Example, F is to F is equals to 1, as F is an extension of field F. Also, so F over F is a vector space and its basis will be E, where E is the unit element. So the dimension of F is to F is 1. Now basically, dimension is basically the number of elements contained in its basis. As it has only one element in its basis, so its dimension or the degree is 1. In the next example, Q root 3 is to Q. Its bases are 1, root 3. So in its basis, two elements are there. So its degree or dimension will be 2. So dimension of Q root 3 over Q is 2. R is to Q is an infinity. This is the case of an infinite extension. As R is an extension of Q, so RQ over vector space. So RQ is a vector space. R is an infinite dimensional vector space over Q. So R is to Q is infinite. It concludes that R is an infinite extension of Q. Q is the rational numbers and R is the real numbers. Fourth example, C is to R. Complex is an extension of the real numbers, which is equals to 2, because its basis will be 1, I. As C is an extension of R, so C over R is a vector space and its basis will be 1, I. It contains 2 elements. So its dimension or degree is 2. Let's see a theorem related to it. If K is a finite field extension of F and L is a finite field extension of K, then L is a finite extension of F. Means if K is a finite field extension of F, means F is a subfield of K. F is contained in K. Suppose this is F. This is field F, right? So K is a finite field extension of F, means F is contained in K. F is contained in K. This will be K. Right? Now it is saying that L is finite field extension of K, means K is contained in L. K is a subfield of L. So K is contained in L, then means K is a subfield of L. So this will be L. So we can say that L is a field extension of F. Right? L is to F is equals to L is to K, K is to F. Lemma. If L is a finite extension of field F and K is a subfield of L containing F, then K is to F upon L is to F. Algebraic element. Now we will know about algebraic extension. The second type of extension of field is algebraic extension. But before getting to know what algebraic extension is, first discuss what an algebraic element is. Okay, if K be an extension of field F and alpha belongs to K, satisfy a polynomial fx over f, that is f alpha is equals to 0 or alpha is the root of polynomial fx, where fx is equals to a0 plus a1x till an xn to the power n, for a subscript I belongs to f and not all of them are 0, then alpha is called algebraic over f. If alpha does not satisfy any polynomial over f, then alpha is called transcendental over f. For example, pi. Pi is transcendental over the set of rationals but is algebraic over the set of real numbers. Algebraic extension of field. Let K be an extension of field F, then K is said to be an algebraic extension of field F if every element of K is algebraic over F. Means if there exists at least one element, any one element present in that extension, every element of K is an algebraic. If any of one of the element contained in it is not an algebraic, then that extension will be known as the transcendental extension. If there exists at least one element of K which is not algebraic over F, then above extension is called transcendental extension. Right? Now, every finite extension is an algebraic extension, but the converse of this theorem is not true. That is, every algebraic extension of field is not always a finite extension. Now, this is all. Thank you.